Uh, is started. Okay, so let's start. Steve, please start.
Okay, thank you, Haita, for the opportunity.
Yeah, okay, very nice.
I'm going to talk about transitivity in humans and non-humans from a category theory perspective. The intent to ask what does transitivity in humans and non-humans tell us about the evolution and development of reasoning? So in the first part of the talk, I'll just introduce the basic transitive inference paradigm and what it means for this question about reasoning. Now, there are two basic forms of it, one called implicit transitive inference and one called explicit transitive inference. I mean, transitivity has been studied for decades. It was originally thought to be a capacity that was unique to humans, but then subsequently many studies have found some form of transitive inference in non-humans, which raises the question to what extent are the two forms related. We're going to take up this question from a category theory perspective. Transitive inference is about relationships between stimuli, so an inference. If you know that, for example, John is taller than Mary and Mary is taller than Tom, then you can infer that John is also taller than Tom. Now, from a category theory perspective, the key approach is, the key word here is profunctors. And from this perspective, we can see that there is some commonality between the two forms of transitive inference via this notion of transitive closure. And then and in the final section of today's talk, I'm going to go back to the original question. And from this category theory perspective, what does this tell us about the relationship between these two forms of transitive inference in humans and non-humans? Okay, so I'll start by introducing the two paradigms. Now, for this slide here, I just want to emphasize that it's been the itself has been studied for many, many years, and there are many, many results. There are two basic forms, so-called explicit TI, originally thought to be unique to humans, and then worked by many people, in particular Graham Halford and Glenda Andrews, looking at in humans and from a developmental perspective. And it appears to be available, or children have the capacity of this form of inference from about age 5, median age of 5. However, it's also been studied in many other species, including monkeys, rats, birds, and fish. And this form is called implicit TI. The key question here is whether or not the observation of implicit transitive inference in non-humans is in some way a precursor to a reasoning in the form that's found in humans, or are they really two entirely different capacities, as some people would argue? The question is, are they same, different, or some combination of the two? That's what we're going to take up from a category theory perspective in this talk. Now, so what is the paradigm? Well, let's look at the implicit form. It's a reward-based paradigm. So what you do is the paradigm consists of in a 5-term series version, it consists of 5 unique stimuli. Let's say colors, for example. What you do is you train the participant to recognize that adjacent pairs, like you reward an adjacent pair like AB, for example. So when presented with pair AB, 2 stimuli, AB stimuli, you reward the choice for B, but not A. Okay, so, and it can be in any order. So you present AB. If they select the B choice, then you reward them. If they don't, you do nothing. And then you present B, C, D, C, and CD in any order, but they're called the premise pairs. And the key test is the non-adjacent pair BD, which you present. Now, if after training on the adjacent pairs, then given the non-adjacent pair BD that they respond with B, then that's taken as evidence of transitive inference. Okay, so you reward B over A, you reward C over B, therefore you should reward C over A, and so forth. Okay, so that's the implicit form, and that's done for, has been done and shown for a variety of species, and also in humans as well too, of course. Now, the explicit form is a little bit is similar in some ways, but a little bit different in important ways. Here I'm using the paradigm as developed by Graham Alford and Glenda Andrews, which is an extension of what's been on earlier work. And in the explicit form, what you do is you present, and the table down below gives you an example of this. You present the premises as ordered colored blocks, two block towers. For example, there are 5 blocks, so red, blue, brown, yellow, green. And then you present the adjacent pairs as 2 block towers, say a red block sitting above a blue block, a brown block sitting above a yellow block, and so forth. So there are four 2 block towers. And then you give them the test pair. And again, it's the non-adjacent BD one that's crucial. And you ask which is higher, which of the 2 pairs is higher, consistent with the blocks. So if you're going to construct a tower made of these smaller 2 block towers, which of the 2 blocks would sit above the other one? And in this case, you would infer that the blue would sit above the brown from the basis that red is above blue, blue is above green, green is above brown. So when you align them that way, blue would be above brown. Hence, the first time response on the BD pair is again taken as evidence of TI. So they're the 2 basic paradigms. And what we want to do is, the question, getting back to the question, is to what extent is evidence of transitive inference in non-humans a precursor for reasoning in humans? So let's look at from the experimental point of view, there are some similarities and there are some differences. Similarities are that both paradigms involve 5-term series, and the crucial test is the non-adjacent BD pair. And crucially, although they're given feedback on the adjacent pairs, they're not given, it's their first time performance on the BD pair that's taken as evidence for transitive inference. There are, however, some crucial differences in these paradigms. And the first 2, one is that in the reward-based form involves what's called multi-shot learning of the data, whereas in the explicit form, it's only 1 shot. So in the reward version, you're repeatedly presented with, say, the adjacent pairs like BD, BC, AB, BC, CD, and DE until you've learnt the fact that B is rewarded over A and C is rewarded over B, and so forth. Whereas in the explicit form, it's just 1 shot. So you're presented with the entire set of 4 premises at once, and you're given the test pair, asked to make an inference, and then that's the end of the trial, and a new set of blocks and premises is presented, and the task is repeated. So there are 2 crucial differences there. One is in the training, multi-shot versus 1 shot, and in the task itself. So in the implicit form, it's just a single transitive inference that you're testing for each individual, whereas in the explicit form, it's a series of tasks, all with the same transitive inference structure. Okay. So they're the basic experimental differences. And so that's the introduction to the basic paradigm. And now in the second part of the talk, I'll go through and look at this, do a comparison and contrast of these 2 things from a category theory perspective. Now, the key point here is that what we want to do is place both paradigms into a common framework. And we do this by what's called categorifying the notion of a relation in terms of a corresponding notion of relation in category theory, which is called profuncta. The profuncta here is the crucial term, and profuncta composition are crucial for this the way we're going to do that. This method is generally called categorification. The basic idea is you take your normal set theoretical ideas and convert them or generalize or abstract them into category theory ones for the purposes of doing the comparison. The idea is you try to reveal commonalities which would otherwise be obscured from a set theory perspective. So to do this, what we're doing is going to look at the analogy between sets and categories. For this particular case of transitive inference, there are a few things we have to do for people not familiar with category theory per se. And so starting from the beginning, we look at sets as a category is a kind of set, a generalized notion of set. Functor is a kind of generalized notion of function. Profunctor then is the generalized notion of relation. And what we want to do is actually talk about profunctor composition. And to do that, we need to talk about enriched profunctors, which we'll talk about in a second. The basic idea is that we're going to apply this category theory to the notion of transitive closure. So the critical issue about transitive inference is the relation itself must be transitive. So I mentioned in the introduction that we can set, for example, the taller than relation is transitive. For example, if I say John is taller than Mary, Mary is taller than Tom, therefore you can infer that John is taller than Tom because the taller than relation is transitive. However, not all relations are transitive. For example, the parent of relation is not transitive. So if I say John is taller than Mary, if I say John is the parent of Mary, Mary is the parent of Tom, we can't infer that John is the parent of Tom because it's not a transitive relation. However, every relation itself can be converted to a transitive relation by this process of transitive closure. Now, in the set theory version of that, we can do this by multiplication of the incident matrix. So you represent the relation as a matrix, and you multiply that matrix by itself to get the inference. Now, what we're going to do then is the category theory version of that, which is composition of the enriched profunctor, as a way of comparing these two forms of transitive inference. And then from that, we can assess to what extent implicit transitive inference is really the same or different from explicit transitive inference. The key point here will be, yes, there are similarities, and specifically they both involve a form of transitive closure, but there are crucial differences between the two paradigms, which speak to the differences between human and non-human cognition. Basic point that I'll be making today. Okay, so to get through this, I won't go through all the details here because there are quite a few, but I just want to give you a basic feel for how to think about this. There are many ways to introduce category theory, but I'm going to do this by analogy. So you can think of, to start off, we need to understand the notion of category and functor. So we can think of category and functor as a kind of generalized form of set and function. So where sets are just a collection of elements, categories you can think of as collections of elements plus some explicit notion of relation between elements. That's this concept of arrows. And therefore, a functor is like a function in the sense that it maps the elements, but it also has to map the arrows between the elements as well. So hence, if you look on, I'm going to say that set is the category as function is the functor. So we have this notion of elements corresponds to the notion of objects in a category. The relationships between the elements are captured by this notion of arrows between objects. And therefore, the functor not only has to map the objects, but it also has to map the arrows as well. So there's two components to the notion of functor. And this is really the essential difference that we're going to focus on today, is this explicit modeling of the relations between the elements, i.e. the morphisms. Now, what we want to do is get to this notion of profunctor. To do that, as a sort of generalized notion of relation. Now, to do that, we need to look at the notion of the relationship between a univariate function and a bivariate function. So this should be fairly familiar, but a function is just a map between sets. Well, a bivariate function is just a map between a pair of sets, or the product of two sets. In particular, the product of two sets is just a set of pairs, it's shown up here. So the relationship between set and product set is analogous to the relationship between univariate function and bivariate function. And this leads up to the relationship between functor and profunctor that we're going to come up into the next slide. The key point I want to point out here is that functions and relations are quite closely related, in the sense that every relation can be construed by as its characteristic function. So, for example, if two elements are related, if an element in set S is related to an element in set T, then we map the pair to the label 1. If they're not related, we map it to the label 0, saying it's not it's called its characteristic function. This is the way we relate functions to relations. And by analogy, this is what we do for profunctors. So profunctor is really the category theory version of a relation. So by analogy, function is to relation as functor is to profunctor. I won't go through all the details here, but the key point here is that whereas a functor is a map from a category to another category, a profunctor is a map from a pair of categories to the category set. And it works somewhat analogously to the notion of relation, except that we've got to take care of also of the arrows between these pairs. So just briefly, what's happening here is the domain now of the functor is really this collection of pairs of objects from the two categories that are being related, and plus their pairs of arrows. So notationally, you'll see the notation for a profunctor looks like this. It's got this arrow with this mark through it. They're not meaning that the arrows are not explicitly here, but they're actually, their relations are captured by the notion of the product of these two categories into set. So we note it either way, but that's the reason for that. So it's not unlike a functor, which is a direct mapping from a category to another category. This is really a mapping from the two categories themselves into the category set. By analogy to the way that relations are like, by analogy, by the way, functions are like relations in the same sort of sense. So with that in mind, once we have this notion of profunctor, we need to have a notion of composition of profunctor for this to work. And for that we need to look at how we need yet another generalization from monoid to monoidal category. A monoid is really just a set with some multiplication operation over it. So, for example, integers with the normal arithmetic multiplier is an example of a monoid. Well, again, this is another example of categorification where we abstract from the notion of monoid to monoidal category. So instead of taking the set, instead of looking at sets, we look at the set M, we look at its corresponding category M, and the multiplication now becomes a tensor product, which is just a bifunctor over that category. Somewhat analogous to multiplication in ordinary arithmetic. Okay, so we need that for the purpose of profunctor composition, and this is really the essence of the analogy that we're going to use here, and that is the relationship. The relation is to transitive closure as profunctor is to profunctor composition. We said before that every ordinary relation can be mapped into one of the transitivity property. Well, this corresponds to profunctor composition. And so a specific example of this, in ordinary profunctor composition, which is enriched in the category of sets. So for example, we had a profunctor from C to D and a profunctor from D to E, then you want to have the composition of those two profunctors is one from C to E. And the trouble is that you can't do it directly is because you have this extra term. We call that profunctor is actually a bifunctor from two categories C and D to the category set. So the two things are not directly compatible. So you've got to do something about the intermediate term. And this is what the notion of profunctor composition does. In fact, what we have here, this is just a simple example of in the category of set. Again, I won't go through all the details, but so suppose this category C has three objects, C1, C2, C3, and then category D has three objects. And the profunctor from that is from C to D. It's just the relations between these. So you can think of C as, say, cities and D as destinations. And the arrows are just paths, how to get from C to D. And then D to E is the same sort of thing. And when you do, what you have is the composition of these is all paths from C to E through D. So for example, you get from C1 to E1 via D1, or you can get it via D2, and that's why you get these two arrows here. John Bez's notion of profunctor composition has an analog in quantum theory called path integral, the path integral, for those people who are familiar with it. Now, the point here is, notice that there are actually, the important point here is actually there are two operations happening here. We have to how to combine these paths. So we're combining the first path and the second path to get this path pair, and then how to integrate over these paths. And that's the second, in this particular case. Now, that all leads up to the notion of transitive closure in a category theory context and how that works. And again, I'll skip the details, but you can think of this in the category theory context as a kind of generalized form of matrix multiplication. So again, the analogy is matrix is to multiplication as profunctor is to composition. So the way in sort of the ordinary set theory approach, you can think of the relation as encoded as a matrix. So between, say, we have a relation on a set A, then the elements that are related are given indicated by 1. So element A here, A1 is related to itself, has a 1. Element B is not related to element A, so it's indicated by the cell 0 and so on and so forth. And that gives you that matrix M encodes the relation R. Now, if you want to do the closure of that, you can multiply that matrix by itself. So when you do that, the new term, for example, if A is related to B and B is related to C, then by matrix multiplication, the 0 term becomes the 1 term to indicate that as so. The corresponding thing to do that in category theory is to look at enriched categories. Now, the simple case is where you enrich in what's called the Boolean category, the category of truth values, which is a monoidal category. So again, I won't go through the details, but because I want to get to the discussion point. And the point to note here is the analogy between matrix multiplication and profunctor composition. So notice here that you have two matrices. In fact, the matrix multiplied by itself. You have the corresponding thing here as the profunctor being applied to itself but via the tensor product. So here, multiplication of matrices corresponds to the tensor product, and the sum over the terms in matrix multiplication corresponds to the coproduct here. Okay. And by doing that, we get a corresponding notion of transitive closure in the category. Now, here, this slide is the point of doing this comparison. We can go back now to the implicit form of transitive inference and the explicit form of transitive inference, and encode that up as two profunctors with the appropriate tensor product. And by doing that, we get the inference, the inference in both the implicit and explicit forms. So it both involve composition of the profunctor with itself to get the inference. They just differ in the particular details of the underlying profunctor, and that's the way the comparison works by a categorified form of transitive closure. Again, I won't go through the details. We can discuss the details later. Point is, I want to get to the remaining few minutes. I just want to get to the discussion of what this means for cognition generally. Okay, so we said that what the category theory shows us is that both forms of transitive inference, as the implicit and the explicit form, involve a categorified form of transitive closure. Okay, that's what makes them common. However, having identified the commonality, that leaves the remaining differences. There are two, and so this diagram down the bottom here really just conceptualizes the relationship between implicit transitive inference on one side and explicit on the other. So the common process here is transitive closure. However, there are still two crucial differences, which you can see from the differences in the original experimental paradigms. And one is that the first one is that the encoding of the original relation slow. It takes a repeated reinforcement learning in the implicit case, but it's fast in the explicit case. It's just one shot in the explicit case. That's one thing. So the binding or the encoding of the relational information, i.e. which item comes before the other, which Q comes before, which Q is slow in the implicit case, but rapid in the explicit case. The second difference is that in the implicit case, it's just a single instance of transitive inference, whereas in the explicit case, it's really what the subject is really exploiting is the transitive inference schema. Okay, and so for the rest of the talk, well, this slide just says what that means formally. I think I'll skip this slide and just go straight to the discussion. So the paradigmatic differences between implicit and explicit are, okay, in terms of training, implicit form requires repeated reward reinforcement for the subject to learn the premise relations, whereas in the explicit form, it's just one shot. And the task itself in the implicit form is just a single transitive inference, whereas in the explicit form, it's after each inference, the new premises are constructed, new colored blocks are presented, a new order is given, and a new inference is required. And so in terms of time, it's slow versus fast. In terms of space, we'll call this one morphism versus two morphism for reasons I'll explain in the next slide. From a computational representational perspective, you can think of it as four aspects. There's the encoding of the premise relations, which we assume in this analysis because the procedures themselves cannot progress until the subjects have shown that they understand the original premise relations. There is a completion aspect. So once that is combining the premises to complete to complete the missing elements. For example, combining the AB and the BC to infer to create the AC pair, in closed form. And then once you've done the completion or the closure operation, then inference is just application of the non-adjacent pair to that representation. And then there's a fourth aspect of the schema itself. So the analysis I've done so far just concerns the completion and inference aspects, and I've left open the encoding aspect, and I'll discuss now the schema aspect. So the critical point about transitivity is that, as I mentioned in the introduction, not all relations are transitive. As I said, John taller than Mary, Mary taller than John, so you can infer that John is taller than Mary simply because the taller than relation has a transitivity property that illustrated by the schema above. By contrast, the parent relation is not transitive, so you can't make that inference. And now the issue here is that preference or reward, or preferential choice is not a transitive inference. For example, in the game paper, rocks, scissors, or gu choki para in Japanese, paper is preferred over rock, a rock is preferred over scissors, but scissors is not preferred over rock. It's a circular relation, it's not a linear relation. And thus, preference itself is not transitive per se. Whereas in the explicit form, in the feedback, subjects on practice trials are given feedback indicating what is expected of them. Okay. So from the perspective of transitive closure versus transitive inference, is that you have an arrow A related to B, B related to C, but you don't necessarily have this arrow between A and C, whereas in the transitive case, you always have this case. So we're talking about essentially we're talking about two different structures, whereas the closure operation converts this structure here into this not necessarily transitive relation into one that is transitive. And it's this difference that's crucial, I think, for looking at in what sense transitive inference in non-humans is really not the same as transitive inference in humans, at least in the explicit form, as exemplified by the studies by Graham Halford, Glenda Andrews, and their colleagues. And so in this slide, what I'm trying to capture this difference here in terms of what I'll call compositionality, or that is the dimensionality. What we're saying here, and then this relates to two things: the notion of relational schema induction, a paradigm developed by Graham Halford and colleagues, and some recent work that I did with looking at that in terms of what's called Tanakian reconstruction theory, or the category theory version of that. And the point here is that there are really two aspects. This relates to what's called dual process theory in psychology. There are really two aspects to transitive inference: an implicit aspect, that is the task level, task instance level, and an explicit aspect where the tasks are compared for their common structure. And the idea of Tanakian reconstruction is that by comparing the task instances, you can reconstruct the common underlying schema. Now, in the implicit TI case, you're not really given that opportunity because you're only ever tested on individuals are only ever tested on a specific task instance, whereas in the explicit form, you're given multiple task instances, and hence the opportunity to compare the structural relationship between these two task instances, and hence the underlying schema. so we've done this in another task, another kind of task that was developed by Graham Halford and colleagues. And the point here is that the transitive inference has a similar sort of style. And so from a category theory perspective, this comparison is really what's called a natural transformation. And a natural transformation is what's in category theory regarded as what's called a two-morphism. Okay, so the individual tasks, Ti, Tj, are relations, are Q-target relations, stimulus-response relationships. And what we want to do, the schema is in fact obtained by comparing these. So the task itself is a single arrow. The comparison is two arrows, so you've got an arrow between arrows. And so structurally, what's going on here, at least from the explicit point of view, is what we might call a dynamical two category. So you have this rapid change, binding or rebinding of relational information, but you also have this spatial aspect in terms of the underlying schema. So from a category theory perspective, we can talk about in terms of zero categories, one categories, two categories. Implicit will be regarded as a one category, like the category of sets and the category of relations. A zero category is just a set itself with no morphisms. Now, a two category, like cat or prof, has both one morphisms and two morphisms, that is relation between relations. So the key point here, or the sort of conceptually what's going on here, is that whereas implicit transitive inference can be regarded as sort of a test of relational information, what explicit TI and what differs between humans and non-humans is that it's relations between relations that's crucial. Okay, and the final slide then, so to wrap up, is this I focused on transitive inference, but this is really part of a much larger story, I think. There are various ways of looking at this. I'll just highlight two because the participants of this stuff. Some people are very interested in consciousness and qualia and the quantum approach to cognition. Now, this notion of and so we had looked at this from a variety of ways, but there's a lot of commonality between what's going on here. Notion of implicit versus explicit has been done also for transitive inference in humans. Humans do both forms, and this can be compared to the induction of structure, which we had done on another kind of task, not transitive inference per se, but we also noted that in the implicit form, people fail to obtain the requisite kind of generalization when they weren't aware of the underlying structure. And this relates to this notion of induction of rational and schema induction and the category theory notion of two category versus one category. Also note here, there are some other things to note here, which perhaps I'll finish up and discuss later, but the notion of qualia as Nao and Hayato have discussed in terms of Yoneda dilemma. It is also potentially related because the Yoneda dilemma is quite closely related to the Yoneda functor, and you'll note that the Yoneda functor is actually a form of, is related to a profunctors has a very similar structure. So there's opportunity there. Hayato has also done the categorical algebra, which is quite interesting in its own right. You can think of it as a categorification of algebraic structure ring, which has two operations, a multiplication and a generalized multiplication and addition, very similar to, in some sense, to profunctors. So there's interest there. But I think I'll just finish there with this notion, leave you with the idea that, sure, there is some similarity between implicit and explicit transitive inference, but there are some crucial differences. And so I would conclude that, yes, there is some overlap, but there is still significant difference. There's a bunch of references to this kind of stuff, which I'll just put there, but I think I'll leave it at this last slide here and open up for discussion. There. Thank you.
Thank you. Thank you for very exciting talk. I have much to talk with you, but first, let's ask anyone comments or questions? Okay, now.
Yeah, thanks, Steve. I'm also interested, but I also found several things unclear. Can you explain a little bit more about the binding time and also schema space stuff?
Yeah.
That part I didn't really understand.
Yeah, I that part was not part of the analysis. So the point was that once the binding part, okay, so what we have to do is go back to the actual paradigm. The binding part is really just speaking to the differences in the paradigm itself. Okay, so I went over this a bit too quickly, but the key point about the experiment, one of the key differences between the implicit and explicit form is that in the explicit form, that you're given these premises, for example, red block sitting above blue block. So you know that red is higher than blue, and you're given brown is higher than yellow, and green is higher than brown, and so forth. So this is just a single trial, and then you're given the pair that you have to compare. Now this is just a single trial. Once you've made the inference that blue is actually higher than here, because blue sits above green, but green sits above brown. Once you've done that and you've responded, then an entirely new set of premise pairs and a test pair is presented. So the binding, what I mean by binding is you have to bind these Qs, red block and blue block, to some sort of, the relation higher than or above or below or something like that in one shot. Okay, you're not given feedback beyond just that one presentation. Whereas in the implicit case, this AB pair or the BA pair and your response is done multiple times before you're given the non-adjacent BD pair. So that's what I mean by binding, is that the red block and the blue block have to be bound to the relational schema itself, i.e. Some abstract notion of above and below. In the other work that I've done, I don't mention this, but that's what the pre-sheaf stuff will be about. That's what I meant by the binding aspect of it. Is that less clear?
I see. So maybe to rephrase that, the binding in the case of the implicit is binding by excessive learning. But right. Binding in the case of the explicit is to hold it in the working memory or short-time memory. And right. Each trial you kind of shuffle things.
That's right. Each trial you'd use new colors, possibly new colors and new orders. Yeah. So the schema here is the abstract notion of relation getting bound to the particular task stimuli. So that's what this arrow here is.
I see. Again, this schema is kind of reshuffled or initialized every trial.
The schema, the underlying, the schema itself is constant. That's the underlying thing. It's the binding between the schema and the task instance. So in task one, it'll be this. Task two, it'll be the second map here, and so on and so forth. And the idea is that this is all implicit. You're not actually told this, but what you do is from the individual, by comparing the individual tasks, this arrow here, you can reconstruct the underlying schema. So this comparison, this arrow, horizontal arrow here, is actually these component arrows here. This is the natural transformation. And the task itself, this T1 here, is actually this arrow here. So there's a bit going on here in this slide, which needs to be unpacked. But yeah, that's. So the dynamic part here is this binding change, rapid change here.
I see. So in other words, if I understand correctly, then the explicit case is like first you learn the rule and then sort of put the item into the slots that correspond to this rule, and then you generate the answer. But in the case of implicit, you don't necessarily understand the underlying rule or schema, but you just apply the individual facts. And then based on that, you actually make some kind of prediction.
Yeah, exactly. Yeah.
Okay. All right. Understand that.
There are no arrows here. Just this one and then you move on to the next one, and then you move on to the next one. And the important, it's a good question. And the importance of all this is to relate this back to the notion of relational scheme induction paradigm that was developed by in the older literature in psychology is called learning set theory, where you do the same sorts of things with animals. But the problem is that the amount of transfer varies with species. Some species can pick it up really quickly, and some species can't. It's this sort of accelerated learning. And what Graham Halford and colleagues did was say that, well, in fact, you can generalize this kind of learning set idea, originated with Hollow is a classic study. You can do this more generally with more complex schemas. And the idea in the original study, Halford and Wilson, which applied the category theory approach, did this with a monoid structure or a group-like structure, not transitive per se. And the importance there was the complexity of the underlying structure also had important implications for development. Younger children couldn't do it where older children could. There's a whole bunch of experiments that Graham Halford, Glenda Andrews, and colleagues have done showing this similar sorts of relationships. And then we did the analysis of this in category theory approach in our 2009 paper, and then this is sort of, but not, and this is sort of another step beyond that.
Okay, thank you.
Yep.
Any other questions, other comments? If not, I will I will do some comments about one of your fascinating idea is to think the Tannakian reconstruction as some kind of the jump from the implicit transitivity to the explicit one. And it's very, how to say, in harmony with my intuition about the development of the cognition. That means some kind of meta view of the metacognition can be represented as this some kind of Tannakian reconstruction is very nice idea. Because, for example, as Ojima is here too, stress that in quantum field theory, Tannakian reconstruction is used to reconstruct from the how to say it, macro to micro reconstruction, like data from the particles, experimental data, scattering data to the inner symmetry or the Bose field to the Fermion field, which is invisible. This kind of reconstruction is very important from the viewpoint of the generalization of the induction process, induction scheme. So many physicists tend to think that the theory itself can be obtained by the genius insight, the mysterious insight. But Ojima stressed that this induction scheme itself is very important, and we should start with data to this kind of theory, and the Tannakian reconstruction can be used to model this kind of procedure, induction procedure. So Steve's idea is a kind of parallel that's not physics, but more general, and how to say, the children can do this kind of Tannakian reconstruction maybe. So it's very interesting.
Yep.
How do you think is there some possibility to check this kind of Tannakian reconstruction is done by children, infants?
So the not for the very young, but in the paradigm developed by Graham Halford, where is it? These two studies, the 1998 and the 2007, was designed for this kind of task. And sorry, and the Halford and Wilson, the original one, 1980. So the younger, it's around age 5 or 6 seems to be critical. So before then, the answer is they can only a very simple kind of inference, where the more so in their case, they used a cyclic 3 group or the Klein 4 group as their basic structure. In the cyclic 3 group, you just have three items. So A maps to B, B maps to C, and C maps back to A again. And so the younger children and you can have like cyclic 4 and so forth. So the younger children couldn't do it, but the older children could. So the answer is interesting in the sense that development involves both. To say that development involves both the induction but also the maturation aspect of it as well. And that's been the basis of Graham's work for decades.
Yeah.
So yeah, the answer to your question is yes, you can develop the tasks. The relational schema paradigm was developed for that purpose. And also, importantly, it should be in principle extendable for something like transitive inference. The problem with explicit transitive inference is it requires the basic form or the original form requires some sort of instruction, which you can't do, of course, to non-humans. But if you set it up as a kind of relational schema induction type, so the 2007 paper by Graham and Hufford and Busby was designed for this, so to do the induction without having to require, in a non-linguistic way, so set it up like a more traditional learning set style approach. Yeah, you can, in principle, do it. You expect the younger children not to be able to do it, the older children would. But it also depends on the sort of nature of the. Obviously, for example, if you use a cyclic group which has more parts to it, like a cyclic 4 versus cyclic 3 or cyclic 5 and so forth, which is what they did in the Busby study. Yeah, it becomes harder because there are more parts to the schema.
Yeah, related to that, and another important idea is the categorification as a developments, like from one category. As you pointed out, the birds or fishes, some fishes can do one category, and the two category, from one category to two categories is very important step to the human recognition. And my hypothesis is a human is a categorical animal. That means a category, as you know, the category of category is just a very typical example of two categories. And the most essential step to the category theory is to recognize the natural transformation, the very typical 2 arrows. And in the collaboration with Shigeru Taguchi in Hokkaido University, a philosopher, we developed some arguments about the importance of natural transformation in the development of ethics, moral. That means that to change the viewpoints, like functor is some kind of representational model, and the natural transformation is a change of the model or change of basis or something that if we cannot do this kind of transformation, we do not have ethics. This is our hypothesis, and I think it is quite exciting that if we can check in what points this two from one category to two category, that like natural transformation comes out, is very quite important and interesting to check, and in harmony with the development of such a moral or ethical developments. So maybe this implicit to explicit or one category to two category or this kind of point is very important. And maybe, yeah, I think we should relate with contact with some kind of ethical developmental researchers. Like,
yeah, I think that
Moriguchi-san also know something. Yeah.
Yeah, I think that's a good point.
Yeah.
But I'll let someone else speak first.
But maybe okay, Steve, please.
Yeah, so I think that what you said is maybe quite closely related to what's called the theory of mind paradigm.
Yeah.
So where person A has a model of person B has of some other scene, and Graham Halfer and Glenda Andrews actually in her PhD thesis and actually this paper. Oh yeah, the 2002 paper. I think they also employed theory of mind for on the developmental side as well. And again, a similar sort of pattern where the can do one step, but not two. Can not integrate the two step. Have a model of someone else's model and so forth. But yeah, quite possibly related to what you just said about ethics, developmental of ethics.
Okay, I have another comments, but please feel free to ask anything to the Steves. It is very good occasion to ask Steves about category theory to the cognitive sciences or anything.
Yes, in particular, any of those slides. I raced through all the slides and there were way too many details. So
Yeah. You can ask anything about the details or now you have anything more?
Can I?
Okay, Moriguchi-san, please.
So yeah, actually related to the Saigo-san's point about moral development. Actually, I don't clearly understand the point, but so Saigo-san's point is natural transformation is related to the moral development, right? So
yes. This is my
defiance is a perspective or something.
Yes.
So which right? So actually, I still don't understand. But yeah, there is a in moral cognition. Also, there is a implicit moral cognition and explicit moral cognition thing. But I guess the sorry, I don't really understand. But similar structure can be applied to the moral cognition as Steve has mentioned in this talk. So yeah.
I don't really understand what you say, but I think I agree with you because I think the moral development has many steps. Very first step in like a baby can have some moral that is maybe implicit level, but in some points it will some phase transition, like more universal ethics, like.
So in that point, you mentioned that natural transformation is related to the such.
Such kind of higher level ethics. Not necessarily the related to the elementary theory of mind, like a mother and me or something, but like to think everyone or something, anyone help anyone or something, or such kind of anyone-ness related to that.
So you mean third person perspective or something? Maybe.
Yeah, maybe third person, but this third person is not such a particular third person, but some kind of abstract or the universal third person, which can be me, can be her or something. So it is very, for me, it's quite in harmony with Tannakian reconstruction. That means Tannakian reconstruction is some kind of reconstruction theorem that from the representation of an abstract group, for one group, we have many representations. And Tannakian reconstruction is to reconstruct this category, category of representation to the original abstract group. So implicit means this category representation category, and to have some scheme is reconstruction form. So if we can do something such like we have some universal scheme or something. So I think that this is a very important point to link with Steve's talk and such a moral development.
Yeah, that's interesting. Thank you. Shia-san, mute.
Shia-san, now?
I can't hear you.
Okay.
Can you hear me?
Yes.
I was thinking, what would be the sort of the underlying mechanism or substrate that distinguish between this, children before 5 or animals versus human, and if you can actually say something about this kind of question from this type of analysis, that would be actually interesting. Do you have any idea? One thing I was thinking is that the difference seems to be something like about the generalization, right, from the examples, or maybe in a sense, debinding or unbinding of the elements or particular instances to extract sort of the schema that you're talking about. So this kind of unbinding may be related to some kind of, potential like a neural substrate to, separate things. I don't know, but do you have any kind of ideas about this?
Yeah, so, for example, you could look at the implicit as something that's learned in long-term memory, say in the medial temporal lobe, and then the explicit, which requires this moment-to-moment transition, binding and rebinding, as it's, say, the link between medial and prefrontal. So prefrontal often crops up for these sorts of higher cognitive tasks, where it's just moment by moment instantiation of relations. And so, and also, I mean, there is developmental story about how the brain develops over the course of the first decade and the second decade and so forth. These long distance connections between prefrontal areas and say medial or posterior areas and that sort of thing. So, so yeah, I think there is a story to be told there as well in terms of changes in the neurobiology. And people have done studies looking at relational complexity, for example, paper by Kruger et al. And Holyoke's group had done stuff like comparing match to sample versus relational match to sample and so forth, and looking at doing fMRI and looking at changes in the activity, specifically around the usual areas are implicated, prefrontal, parietal, and so forth, but looking at how that contrasting the different levels of complexity and the corresponding activation. So yeah, prefrontal long distance connections implicated there. So, yeah, so there are really two aspects. It's about will be the maturation aspect, but also the induction aspect. Once you have that capacity to be able to actually, from the data, to induce the underlying scheme.
Okay, so how about Professor Hori?
Oh, thank you very much for nice talk. So I'm rather physicist, so I don't understand completely mathematics. However, I'm very much interested in the physical analogy, space-like and time-like.
Mhm.
In that case, in mathematics, if we consider schema, we consider entire world itself, but physically, the schema is very much restricted in neighborhood of space-time. In this case, we have kind of getting mass by symmetry breaking, spontaneous symmetry breaking. We limit some kind of subcategory of schema. In that case, we can very easily apply the explicit recognition, something like that. But if schema is so wide, in that case, we can only do some kind of implicit recognition or something like that. How do you think about some kind of spontaneous symmetry breaking in the restriction of our schema when we grow up? Schema is a little bit narrower. In that case, we can very easily apply schema recognition. And so I'm very much interested in such kind of, so how do you think about such kind of incompleteness of schema category or subcategory about schema?
Yeah, very good question. Thanks for that. I think it's so you can have. There are probably two ways to do it. One is to look at the, well, in fact, even in the Halford 98 and Halford and Busby studies, they don't use the entire cyclic 3 group. In the Klein 4 group case, which has the 4 elements and the 4 actions, horizontal, or diagonal, and identity, they only use 2 of those. So already you're looking at a sub-schema in that sense, or a subgroup, or and so forth. So yeah, so there's that way of looking at it, and you can also look at it from a sort of a higher order. Look at schemas over schemas, or models over models. So this all works in a particular category. So here, the category M sets from it. So you can talk about it like a two category theory of Tanakian reconstruction. Reconstruction is done at a higher level, and so yeah, so there. I think there's some sort of parallel there, although I can't pinpoint what it would be. But yeah, even from mathematics itself, I mean, there is a long evolution or development of all ideas. They don't just come overnight. So you sort of see that there's a gradual enlarging, sort of a, how should you say, a modularization of the miniature schemas, and you can look at relations between schemas to get them more general. So, yes.
Yeah. Thank you.
I think I would agree with what you're saying.
It's very much interesting. Yeah, thank you.
The reason it's sort of straightforward from a neurobiological perspective, think of the neurons as have a receptive field, and but they're quite limited. It's always local. So the kind of the point that I discussed I didn't talk about it here, but pre-sheaf notion here, how you have to. The difference between local versus global information is captured by the difference between pre-sheaf and sheaf. It's the same sort of idea where the neurons have sort of limited field, but then if they don't overlap, well, then you only have local knowledge, but you've got to look at the intersection between the neural fields to make this sort of connection. So yeah, I think it's parallels what you were saying.
Thank you.
So, any questions or comments? We have more time than usual in discussion.
Can I ask?
Yes, of course.
So Steve, so in children study, systemic children perform correctly in some task, but not in other tasks in transitive inference. Like in social domain, children perform better than the domain in physics. So my question is, this structure is domain general or domain specific? So do you have an idea of?
Yeah, it's an important question. So the easy answer is, of course, it's a bit of both. Of course, you'd like to know exactly one or the other. So in the case of the non-human studies where they demonstrate, for example, I should give it to you. The kind of transit inference that they're doing, for example, in the fish study, which is this one here, Grosnick et al., fish can infer social rank by observation alone. The order that they're doing is in a very specific case. It's social rank, which it's a dominant hierarchy. One fish has dominance or is stronger than another fish, and from that they can. So if A is stronger than B, sorry, if A is stronger than B and B is stronger than C, they can infer that A is stronger than C. It's a very specific kind of schema. So domain specific. So, and the same with presumably happens with children as well. But then, at some point, there becomes an increase in the generality of what they're doing. So, domain over which that they can apply these rules expands. Yeah, definitely, it's both. It's just that you can pinpoint. Well, at least with the Andrews and Halford study, where I think they did 6 tasks: transitive inference, class inclusion, I think it might have been theory of mind, and a couple of others. And there's a lot of commonality around the age 6. I mean, it's not exactly, but there's a significant correlation between the different tasks, even though they use stimuli and structures. This ternary versus binary issue popped up again and again. And it's not a hard and fast thing too, of course. You get some 4-year-olds who can do it and some 6-year-olds who can't, and it's a graded type thing as well. So experience is a role, as well as that plays is a factor as well too, of course.
I don't know, maybe this is a question to both Moriguchi-san and Steve, but also Steve mentioned something about the rock, paper, scissors, right? This type of ring-like structure of the hierarchy. That I vaguely remember that there was a study of structures in nature, like if you look at the 3 elements and what is the most prevalent kind of a structure and so on, and then in many cases they do find this type of the structure, like A go to B, B go to C, and C go to D. And but probably it's more prevalent to have A go to B, B to go to C, without A to C, or A to C also present, or something like that. And in the development, is there some kind of particular structures of the 3 items relation that is extremely difficult to learn, or automatically almost always children can learn by default? Like as Steve said, it's not necessarily the case that the A to B and B to C kind of structure doesn't imply A to C normally, right? In the case of rock, paper and scissors, is it difficult for children to learn rock, paper, scissors?
I mean, the study would be, the studies have been done to look at pseudo-transit inference where, but this is for adults. So even adults make overgeneralize the relation. So where the relation, for example, parent of is not transitive, but they still make the inference. And so it's not, it's a fallacious inference. So, even for adults, there is that distinction. So presumably for children, yeah, there is a distinction too. So the test would be to contrast a relation that is transitive versus a relation that's not transitive, and see whether or not they erroneously make the ARC situation, which people, adults do too. I mean, adults also make lots of erroneous inferences that are not strictly supported by the logic. So yeah, to answer your question, no, I don't know, but
Okay.
the top of my head, but yeah, I would presume it's. It's called transitivity of choice by some authors, including Graham and someone else. So you can do the task for animals, for example. So you preferentially reward A over B, B over C, but you do it in a cycle. So A, B, C, D, E, and then you go back again. So E is rewarded over A, so you get the complete cycle. And then you look at the non-adjacent pair like B, D, and see what happens. And some experiments say that they do it, and some experiments say that they don't. So I forget the exact result, but closing the loop can make the whole thing collapse, or not in the non-animal case, non-human studies. So presumably, it would be more difficult.
Related to that, a very small point that glue paper and rock, scissor, and paper structure can be understood as some kind of pre-order, not POSET, but it is a pre-order, like because pre-order can allow this cycle structure. So I think that if we stick to the POSET, then this glue structure is excluded. The pre-order can contain this kind of structure also. And I would ask that as far as I understand, the facts, experimental facts can be understood in the framework of pre-orders. But I completely agree that we should use category, not only pre-order, but by the starting point, as a starting point, the pre-order structure is very good to start. I understand, I agree. But do you have any ideas to have some merits to use general category than the pre-order in this transitivity structure?
Yes, but not immediately, because I think the whole induction is really a core process of higher cognition. So in the previous stuff, I just limited myself to the monoids, but yeah, its theory can be more general than that. So instead of the monoid being the action on the set, you can have some more general category as being the action, and you want to induce the category and so forth. So the short answer is I would like to, yeah, and that would be one way to go.
Yeah.
Again,
yeah. I see that for example, the Tannakian reconstruction, we need a category in general. Yeah, I agree. Yeah. But it is very also it is my interest that to test the importance of the general category, not only the pre-order, to take experimentally test that is very interesting. And I think at least the spatial recognition or something, we have to have many arrows between two things. So what do you think about the similar structure is important in transitivity, at least explicit transitivity? Do you have any ideas?
Yeah, I think it's important, but I don't have a specific experiment in mind. Yeah, I don't have a specific thing in mind, but other than to say, yeah, I would agree. The more general structure is the thing to look at for the more general theory. But I'm just drawing a blank now.
My idea is that to compare this transitivity structure and some kind of spatial or temporal spatial structure. So to see the relationship between these framework of cognition, maybe we have some very important example the general category than pre-order. So
yeah.
like for example, for mathematicians, we have the notion of different proof to the same theorem. The notion of proof is some kind of path from one proposition to another proposition or something. So we have many paths, but it is known that the semantics of the proof itself is very difficult. Provability, semantics of provability, which is pre-order, is more simpler, very simple, but we need some semantics for the proof, not probability. So maybe this semantics, proof semantics, and this transitivity or this transitive inference. So the notion of inference itself should be enriched to how to say not only pre-order to but also so maybe that kind of approach is fruitful.
Yeah, I think one way would be to look at the learning transfer. You think of so if you have some notion of distance of the various arrows. So instead of looking at a single arrow from A to B, you look at multiple arrows, and each arrow has a cost. So that would be one way to look at transfer. So when you do when you go from A to B, a bit like when you navigate, if you at point A, you want to go to point B, and you take a route, and it'll take you, time. But then as you do it again, you might find alternative routes which have a lower cost. And that would capture the notion of some sort of transfer of learning in that sense. So the learning is getting from A to B, and then the transfer is another path from A to B that has a shorter distance. So that would be one way, I suppose, to look at the more general notion of category rather than just a pre-order. You have multiple arrows between the same two.
I think that's a very good idea. And maybe another simple idea is to make use of the free category from some directed graph or more general string diagram, something.
Yeah, I've done that in the context of generalization. So you want to, for example, a grammar can be thought of as the sentences that you can produce from a grammar can be considered as a kind of free category in that grammar, on that graph, I should say. And people have looked at that. I mean, there's some older work by Walters looking at language as a kind of free category in that sense. So the idea being that allows you to construct many more other examples by just continually by generating all the possible paths.
Do you have any questions or comments?
Yeah, so this may be completely irrelevant, but with respect to this kind of cyclic structure and also your comment on the pre-order or not pre-order or something like that, I've been looking into Bell inequality type relations recently. So, but I'm not a physicist. So what I'm saying may be completely wrong or irrelevant. But the core kind of structure there is that when it's like a linear circle, right? That's I always think as a sort of a core structure. A says that B is telling truth, and B says C is telling truth, and C says that A is telling a lie. And then if you try to make everything consistent, then you are kind of like a Möbius ring like structure that A is telling truth, and the lie, truth, lie, and so on. And this kind of thing is related to Bell inequality, where A and B is positively correlated and B and C is positively correlated, but C and A is anti-correlated or something like that. So to make sense of this kind of structure, which locally, it's easy to understand what it means, but you need to kind of, think about it, why this is kind of, illogical or at least not rational in the standard kind of, logic, right? We need to go into some space where this is valid. For us to understand this, then we probably need to have something more than a pre-order, right? Type structure. But I'm not sure whether my thinking is in the right direction or not. What do you think?
Yeah, well, so I mean, even at the very simple level, so the transitive inference case, it's a linear order versus a circle. So I mean, the dimensionality is different even there. So yeah, so
maybe the Berry inequality or something is related to the from 0 category to 1 category, maybe. That means that for the sets, we can consider the algebra of functions, which is commutative. But for categories, we can construct similarly the convolution algebras of functions, which we call category algebra, as Steve pointed out. In category algebra, we have many non-commutative elements. So non-commutativity allows some kind of the violation of some kind of expected coherence to the major theoretical understanding of. So maybe the 0 to 1 is related to the Bell type relation, but also maybe the more higher level from 1 to 2, maybe we have more deep violation, such kind of thing. Yeah, I don't know exactly, but I think it's very good to research.
Okay, thank you.
Do you have any comments or questions? Okay, Steve, thank you for the very exciting talk and everyone for the very fruitful comments. So see you at the next seminar. I will send you an email after the talk speaker decided. Maybe the Mr. Daichi Suzuki will talk on 28th February, and I will send you email about the details. So this time, thank you for attending this seminar.